Good afternoon. Welcome to the Geological Society of London, and to this, the second Shell London lecture for 2013, entitled Landslides and Subsidence: Engineering Geology in an Age of Austerity. My name is Nick Billam. I'm the Head of Strategy and External Relations here at the Geological Society, and it's my great pleasure to thank Shell UK for making this series of public lectures possible. Now, our speaker this afternoon will be familiar to many of you as our current president, the president of the Society, Mr. David Shilston. He normally introduces these lectures in the evenings. One or other of us, the staff here at the Society, often depute for him during the afternoon, but we thought it quite unfair to make him introduce himself. So you've got me, and our evening audience will have our executive secretary, and it's our great privilege to work with David and to welcome him here to give this talk. David is someone who is more committed, I think, than anyone else I know to communicating our science and to inspiring the next generation of geoscientists. And it's a great pleasure to have him talk to us as well as to work with him throughout his 2 years as president. David has 35 years' experience of civil engineering and geological projects in the UK and overseas. And apart from his general knowledge of civil engineering, geotechnics, geology and geomorphology, David specialises in assessing and managing geohazards. And you're going to hear something of that work this afternoon. Now, subsiding buildings, collapsing mine workings, landslides and other problems in the ground affect all of us, as householders and as users of our complex national infrastructure. What we perhaps don't often think about is how engineering geological expertise helps us to eliminate or reduce the impact of these hazards. And a question which I think David will particularly address this afternoon is how should our approach to ground problems be changed or adapted in this current age of austerity? Now, many of you will have seen the bust of William Smith at the bottom of the main staircase out there and admired his geological map that we have on display. Smith was self-taught. He earned his living draining land and building canals. So he was a proper working geologist who got his hands dirty. He was arguably this country's first engineering geologist. Now, the Society did recognise him with the award of its first Wollaston Medal, our principal award, in 1831, but he was not a gentleman. He was a chap who had to work for a living. So he was never made a fellow of this Society and therefore never became its president. And partly as a result of that, David is our first engineering geologist president in our 200-year existence. I think that deserves a round of applause. So you're seeing here the work of a very significant part of our membership, but one whose work I think is largely underappreciated and not as visible as it should be to the public, to policymakers and so on. I think David is also our first president to hold any sort of qualification in archaeology, as far as I know, but I don't know whether that's going to crop up this afternoon. Thank you for coming, and please join me in welcoming our President, David Shilston.
Thank you. Good afternoon, everyone. You've set me a high target, Nick. I'm going to talk about the subject you see on there, and I'm going to try and tackle every word in the title: landslides, subsidence, engineering geology, and austerity. So it's quite a tall order. I've got lots of slides. We'll run through those. There are no equations. There are only a few graphs, but the photographs come from all around the world, from the work that I've done, stolen from the internet with thanks, as you'll see as we go along. All right, training course over. Here we go. Landslides. This is a famous landslide in Hong Kong in 1972. You can see the statistics there. There were a number of landslides at about that time in Hong Kong that led to significant loss of life. This landslide knocked down 2 buildings, 2 tower blocks. And as a result, in Hong Kong, the Hong Kong government set up the Geotechnical Engineering Office, which has significantly reduced landslide risks in Hong Kong. Hong Kong is often described as Manhattan with mountains, and you can see just the problem there. Landslides are complicated things, but they needn't be. This is an extract from a drawing. I'm going to show you the full picture later on. But if you look at the top right, a building has been built on a platform cut into a hillside. The cutting has not been designed properly, so the first orange arrow is taking away the ground above the building. The building has been built on filled ground, that cross-hatched land, and that has failed as well, so the back of the building is broken. The swimming pool, which is this, has leaked, and one of the major causes of landsliding is water getting into the ground. So they've been the instruments of their own destruction there. You can see the drains of the building, the gutter is draining into the ground as well. And just off the picture, an access road is built with a cutting that failed. So this is not a good place to be, and it's what we engineering geologists try to prevent happening. Subsidence is a different but related problem. It's the ground moving. I've illustrated two types of subsidence here. Compression, that is just consolidation of the ground, the squashing of the ground by squeezing water out of the pore spaces, and the Leaning Tower of Pisa is the classic one for that. There, the compression is differential, so the tower has tilted as a result of one part going down more than another. Closer to home, shrink swell is a big problem in our clay terrain in the UK. For example, the London clay. Clays of this sort expand and shrink when water is added or taken away from them. So as you can see, the tree there on the left has grown and is sucking water out of the ground, causing the clay to shrink and the building to suffer. It's a very common problem in southern England and can be overcome by designing the foundations properly or not building buildings too near trees. Another form of subsidence, which is more immediate, is the subsidence due to collapse of the ground. So this is a photograph of the M25 taken by a colleague of mine a few years ago when we were working on the widening of the M25. If you go from Heathrow round to Watford, you pass through terrain like this. The white is the chalk. The chalk is a soluble rock. It has dissolved, leaving cavities that have been infilled by the clays above. So these are clay-filled cavities. If you add water to that, for example, a burst water main or very heavy rain, the clay is washed away into another cavity perhaps, or its open structure collapses, leading to sinkholes. Now, holes in the ground can be man-made, so we have mine workings, but we'll come on to that later on. Let us first talk about the soluble rocks. This is a map from two gentlemen from the British Geological Survey that looks at the soluble rocks in England and Wales. The green is the chalk, as I'm sure you spotted, but the other layer I wanted to point out in particular is this blue layer here, which is gypsum. Gypsum is calcium sulfate. It's very soluble. It's much more soluble than calcium carbonate, which is chalk and limestone. And it's so soluble it doesn't outcrop in the ground surface in the UK. Our weather is too miserable and wet. But it leads to collapse problems. I chose this photograph because it's such a brilliant one. It's a vertical or near vertical aerial photograph of an area in Sussex, as you can see, with sinkholes formed. And purportedly, according to the technical paper, there are 63 sinkholes in this picture, 8 in the gardens, 4 in the road, and the remainder in the field. And some of them are complicated. This sinkhole seems to have sinkholes within it. But this is the important thing, the red circle. The cause of this problem, a burst water main. Water got into the ground and led to that kind of collapse. Think back to that photograph of the M25. It's that kind of problem. Now, if you live in Ripon, you'll be very familiar with this. This is gypsum collapse. The big cavities in the gypsum at depth leading to collapse features, in this case, a bungalow going in. Mine workings are somewhat different. They're still holes in the ground, but they're made by man rather than by nature. I first showed this picture years ago when we had our chief executive, and I flippantly said, "Oh, this is a new Atkins office." Career-limiting move, I think. So Clive Edmonds, whose work this is, I'm just going to illustrate, has spent a lifetime working on these kinds of problems, not only natural collapse in the chalk, but also man-made collapse. Look at the bottom half of the picture. This is a map of possible chalk mining. So in the left is a quarry, and in the wall of the quarry, someone has dug a tunnel to mine chalk, and then we call that an adit. The particular layer of chalk might be dipping deeper, so you would then put a shaft, go down the shaft and bell out like a light bulb, called a bell pit. And that kind of mining is used for coal mining as well as for chalk mining. But as you get deeper and the sophistication of mining technology increases over, say, from the medieval to Victorian period, you end up with a mine rather like the pattern at the bottom there, bottom right. Oh, pardon me. With roadways, a shaft, pillars. And all of this is shown in the top of the diagram in cross-section. You can see the mine is working a particular layer, a particular seam in the chalk. And this happens in Reading. Reading is quite famous for its chalk collapse, Field Road being one of them. You might ask, why are people mining chalk? Isn't there enough of it lying around at the ground surface? The reason being, in Reading, it's got a happy coincidence of good clays for brickmaking and chalk, and you need to puddle the chalk into the clay to turn the clay into perfect brick-making materials. So this could be Ripon. It looks like Ripon. It's basically a house that's fallen in a hole in the ground. But in this case, it's the result of man-made problem. This is a photograph taken from the BBC of one of these chalk mines. The chalk is white, of course. The layers of flint are there, those little black lines. And the scale, the 2 people. So you can see these are pretty big, pretty big. What causes them to fail is that their roofs gradually lose the ability to support themselves. They gradually ravel upwards. So you get what is called a crown hole developing above the gallery or above a particular place in the mine. And Clive Edmonds has produced this rather nice sketch that, as you can see, it's a slightly more artistic version of his simple diagram. Even Field Road is labelled. But these are the crown holes. Oh, I have to get this right in the end. There we are. There's the crown hole. So the gallery in the chalk is losing its roof, and it works up through the Reading Formation, which are just clays. They're not very strong. And eventually that crown hole comes up to the ground surface. The engineering solution to all of this is to fill the cavities with something, with grout, with gravel, with concrete, depending on the nature of the problem and what you can get in there. And that's what's being done in Reading over a number of years now. But mine subsidence can cover much larger areas. That's a localized collapse. And I want to illustrate this for some a case history of some work in Stoke-on-Trent at Wedgwood's Etruria Works. I didn't work on this myself. I did a very, very similar job for the Coal Board years ago up in Lancashire, which is so similar, but because it's a commercial work, it's difficult to publicise. This is well publicised, this case history, and in fact, I've put if you want to go and look it up, it's the potteries.org website. It's rather nicely explained, and they've got some beautiful illustrations, but the principles are there. So Wedgwood opened his pottery. The Trent and Mersey Canal came along a few years later, so he could export his pottery without it being bouncing along the road and breaking. And then over a century later, the ground was mined, deep coal mining in Stoke-on-Trent. And the total subsidence as a result of this deep coal mining was 2.5 meters. And I'm going to show you the evidence for that. Oh, there we are. So this painting is a modern painting depicting what the Etruria Works looked like in the late 1700s when it was first built. As you can see, the canal is at the same level as the wharf and as the factory, and it's a greenfield site. So it's a greenfield site, factory, with its export and its factory nearby. I don't know what this round building is, but bear it in mind, because it appears in the next photograph, next picture, which is a photograph of the factory just before the mining started, before that 1900 period. So you can see the canal boats are the same level as the wharf, the pottery factory girls are there in their white smocks, and this wall here is the wall of leading up to a bridge over the canal. So everything's fine, hunky-dory. The mining takes place, and within a little while, the ground has settled. So this is 1970s. I think the settlement was probably still continuing, but no longer is the canal at the ground level. The canal is at its original level relative to sea level, because water doesn't go up or downhill. But the ground has dropped all the way down 2.5 meters. So that's the drop due to the reduction in thickness of the coal seams being extracted and the mining collapsing. And in fact, the mines are still moving a little bit in Stoke-on-Trent, and every now and then you hear of an earthquake being reported in Stoke, don't you? Just a small, low magnitude rumble as the mines are collapsing. And it's interesting, it's sad really, the factory seems to have all gone, and you're just left with this rather forlorn round building. Let's talk about landslide potential. Changing the subject a bit. You could think about subsidence potential and swelling and shrinking potential by the geology. Where is the London clay? It's here. That's where swell and shrink problems could occur. The same thing can be done for landslides. So this is a British Geological Survey map of landslide potential, ranging from the light pink colour, which is hardly any landslide potential, to significant potential. And because we're in southern England at the moment, I thought I'd show you the Weald. And the geological map there is a simplified version of the geological map, of the one you see down there as well. And there's an intimate connection between the landslide potential and the geology. And in particular, the clays, the clays and, the clays and sands, get it right. The clays and sandstones of the Weald are here. So this is a high potential landslide potential in that area, and also a little bit over to the west. And you can see across the whole of the UK, if, for example, you know the Peak District, and I'll press the right button now, there we are. These are the carboniferous clays in the Peak District that cause the landslides all the way around Stanage Edge up to Mamtor and round back the other side. So they're well picked out and well known. Types of landslides. There are probably more landslide classification schemes than there are landslide specialists. It's just something they love to do, unlike, say, the periodic table. So this is one I've chosen. It's the United States Geological Survey's one. I've chosen it because the pictures are so well illustrated. I'm not going to describe every type. I'm just going to describe some from here. So the first ones I want to describe are landslides that happen very quickly and rockfalls. So if you look at the top left-hand one, this piece of rock has fallen from there in the diagram, and it's fallen because the rock has got fractures in it, discontinuities as we call them, fractures that have broken the rock, and this piece has fallen simply under gravity. Toppling is a similar effect in as much as the rock has fallen forward, but often due to undermining, say the soft blue clay has been removed. So these are fast. Now debris avalanches and earth flows are rather similar in a way, in that they occur quite quickly, but nonetheless they are completely different because the ground is broken up. So debris avalanche is what I really showed you in Hong Kong. And in Hong Kong they're often called channelized debris flows. They move very quickly, meters per second, from a source area top left, as you can see. The soil is, the earth is entrained, and often you end up with a bigger volume at the bottom, say where you put your tower block at the bottom, than you do at the top. Now, earth flows look superficially the same, but they move slower. They might move at a meter per year, 10, 20 meters per year, but they have the same kind of process in as much as you get the ground remobilized there with the addition of water, traveling down here, and then when the gradient drops, it flattens out and you get a depositional area. But these are completely unstructured. There's no structure left within that landslide. This is perhaps the kind of landslide you had in mind when you thought about what I might talk about. These are rotational and translational slides. And in those cases, the upper part and sometimes much of the landslide mass remains sort of intact but broken up. The left-hand one is rotational, and you can see why. There's a curved failure surface, back-tilted blocks at the top, and then a debris zone at the bottom. With a translational slide, translational slides happen where the ground is seriously inhomogeneous, and you have a particular weak layer, and that's what I'm going to try and show you now. That's a weak layer, and this block has slid off the top. And it's important to understand the difference here because we analyze these in a different way. The mathematical analysis of A is different from B. Now, it's useful to think about the speed of landslides, and we colloquially call them whooshers and creepers. So a whoosher is the one on the right there, and both of these are my photographs. So that's one in China, in Shenzhen, just to the north of the border between Hong Kong and China. So it's very similar. It's just a smaller version of the Hong Kong one. Happened very quickly. The materials rushed down and hit the ground at the bottom. This factory, I think, is probably not finished, but it looks like they abandoned it, perhaps thinking about the landslide hazard. And then the one on the left, I can't tell you where it was. I was going to, and I realized I probably shouldn't. Anyway, this is someone's house somewhere in England on a landslide. I've even covered up the number plate of their car, as you might have spotted, to protect. But interestingly, it's a lovely house. It's just leaning backwards. It's in the back-tilted zone of one of those rotational landslides. It's a creeper. It might not be moving much at all. And there we are. So this house here, in this cartoon, is sitting up here. And this is what the engineering geologist tries to understand the mechanism of failure so we can analyse these and design preventative measures if the failure is about to happen, or corrective measures if it has already happened. Rockfalls are interesting in as much as they happen very fast. I don't know where I got this picture from. I've had it for years. But why I use it is that it shows a single rockfall that has ploughed into the ground, missing the bungalow to the right. I imagine this is in the Alps or the Dolomites. Rock is very dense. A motor car weighs nearly a ton. A cubic metre of rock weighs 2.5 tons. So we're looking at an immense weight of rock there that's hurtled down, perhaps bounced over the head almost of the photographer and ploughed in. And the other nice thing about this photograph is that it shows the fracture surfaces. That there, that light colour, is one of the fracture surfaces upon which the rock was released from the rock mass. And this is how we might stop this kind of thing. Fences of the sort you see bottom left, they look a bit like a tennis net, but they're not that at all. They're much stronger, of course, concreted into the ground, tied back perhaps, and they're made of a mesh that expands when you put a, as you see from the top photograph, into the mesh to absorb the energy. So the mesh doesn't behave like a badminton racket with the thing just pinging off, making the problem worse. The idea is that it acts as a three-dimensional arrestor hook to hold the rock as it comes down. But clearly you need to understand the size of rock that you're trying to prevent, in this case, hitting the road below. This kind of fence would not have been adequate to stop the big boulder by the bungalow, of course. So that leads us on to the managing of geohazards. We have to characterise the nature of the problem, whether it's a rotational slide, a big rock falling off, a creeper, a whoosher, whatever it is. So this diagram, which comes from people I work with, Lee and Charman, some simplified this, and I've simplified it still more. You come in at the top, having discovered what the ground conditions are like, and you characterise the problem. What do you do? What are your management decisions for a ground movement problem? And it could be landslides, it could be settlement, subsidence, indeed it could be flooding. And of course, the things you can do is you can either accept the risk, it's not a big risk, you can afford to repair the damage or something like that. You can avoid the risk, don't build your house on ground that's subject to coal mining or whatever, or you can simply reduce the risk by doing something. And the mesh net to catch the boulder is an example of reducing the risks. But this is an important decision. They have different costs, different implications, and different outcomes. And in the background, of course, is the legislative framework. Different countries have different rules for how you might tackle these kinds of things. And then you could do this. This is the only management consultants matrix that I'm going to show. So as you can see, you could think about geohazards. You could think about a landslide or indeed settlement. Is it going to happen fast or slow? Gradual, sudden, whoosher, creeper, that kind of thing. And also, is it going to have a big impact or a small impact? So if you imagine you had a garden shed and there was a cutting behind it and perhaps the soil might fall off, well, that's probably a fairly low hazard scenario, and maybe it's going to happen slowly. So you might do nothing. But of course, the situation down here in the red zone, where you have something that's very important, say a power station with a big rock cutting behind, so something that's very important, whether it's fast or slow, the problem, you're going to have to do some form of engineering solution. So these kind of matrices are the way we go from the ground characterization through the decision into trying to decide what to actually do to engineer solutions. Now let's talk about a real project. One of the pleasures of my job is I'm paid to go and see the geology because it doesn't come to see you. So a few years ago, I had to visit this pipeline job in Peru, the Camisea pipeline. I've chosen this map simply from the internet because The Economist, from whence it comes, make brilliant maps in their magazine, and it does explain very clearly what's going on. The gas fields for which these two pipelines carried gas and liquids are up here at the top of the Amazon basin. I was surprised to discover that Peru goes right across the Andes to the other side into the jungle. So the pipeline comes right across the Andes and then across the Atacama Desert to a handling terminal you can see near Pisco, and then off to supply gas to Lima as well. And it's a long pipeline. This is the kind of terrain on top left that the pipelines have to cross. And here they are. There are two of them. One is gas and one is liquids derived from the gas in a trench. But why I'm talking about it is this statistics I've given there. So in the first 30 months of operation, this pipeline system had 6 ruptures, and 4 of them were due to landslides. And we were employed to advise on one of those landslides, and I'm going to show you that now. Routing of pipelines in mountainous terrain is really quite tricky, but the basic rule is stay up high, stay on ridges and spurs. And the reason is perhaps obvious, is that on a ridge and a spur, the top of the ridge is normally quite stable. But on either side, this is where the landslides lurk. This is where the big erosion occurs. And it's very difficult to put a pipeline through there. So staying on ridge and spurs is what you need to do for pipeline routing in rugged terrain. But ridges don't go on forever. Spurs don't go on forever. You end up down in valleys sometimes, or sometimes they're just too difficult to put a pipeline on it. And that was the situation in this case history. So here's my rather grainy photograph out of a helicopter window. I'm pretty sure I've not exaggerated this vertically. It is precipitously steep. Down here is the river. Up here's the slope. Right up there you can see a ridge profile running right up, way up into the ceiling. And the pipeline designers could not put the pipeline over the ridge that's in the cloud uphill of the photograph, as it were. So they built the pipeline in this road, in the previous road that connected a number of villages. So this is broadly a contour line. And the landslide, the pipeline ruptured where they put the red egg, in an area of shallow landsliding, but I'm going to show you that on the next slide. This is a cartoon that describes what was going on. The bench of the road was built. They pushed the spoil off to the side, and if I flick back, you can see the environmental damage done by pushing spoil off the side. Deforest the ground very severely. And then, subsequently, years later, a pipeline is put in the road, and it failed by a shallow landslide of that rotational slide I've shown with the 3 upper arrows. And that was what was thought was to be going on before we got deeply involved. It became apparent, however, not only had it failed like that, but the whole of the hillside was on the move, and that's why I've drawn that red line parallel to the top of the fractured bedrock. All the weathered rock and near-surface geology, superficial deposits, is on the move on that hillside. And that's a photograph taken from the ground, looking across to the area of failure, which is here. That's where the pipeline actually failed. But if you look up here where I put the red arrow, that looks like the back scar of a really big landslide. So they've just nibbled away at a much bigger problem. What did they do? Well, just before we got there, they started to do this, which was to insult them, as they're not here to defend themselves. We could call this gardening. It was just an attempt to keep the road open and to stop the small landslide from making matters worse. So they put gabions here, rock baskets filled with stone by that red triangle, and the other red triangle shows a small piled wall they put in by basically driving scaffolding poles or something like that into the ground with planks in between, just to stop the very shallow near-surface material moving. A quick fix. They also did this, and this is a photograph a little bit round the corner. They took the pipe out of the ground and put it on sandbags. Took the 2 pipes out of the ground and put them on sandbags. So that even if the ground is moving fairly slowly, they can see what's going on. They can use the digger or crowbars to keep the pipe intact. So that you could argue was a medium-term fix. But clearly it's not a long-term fix. So they go through this kind of thinking, as I've shown you before. So initially, the project accepted the risk of landslides by putting a pipeline in sidelong ground along a road. Clearly that didn't quite work, so that the immediate remedial measure was to reduce the risk, take the pipeline out of the ground, do that little bit of small engineering work. But the real solution is to avoid the risk, and that's what they did. They made a tunnel, which you see top left. They made a tunnel through the hillside, underneath and behind the landslide, and put the pipeline in that. So they completely avoided the risk. Tunneling is quite common in pipeline engineering. It's just immensely expensive compared with digging a trench and putting the pipe in there. So, age of austerity, we had to get there in the end. How much austerity? And what about climate change? As I was preparing this lecture, I began to realize that we're in what you might call almost a perfect storm. We've got climate change happening at the same time as our country is going through a period of severe austerity. So I want to take these as two sub-themes and to try and answer some of these other questions that I put up there, and to point out that small problems have big consequences, and we need to decide in relation to austerity, climate change, and the small problem difficulty, how we spend our money, and what we as professionals, my engineering geology colleagues and I, do to respond to this situation. I am not an economist, so I was a bit nervous about what I should put up about this. So I decided to quote a meeting that was held at the Treasury. Well, you can't get better than that. And it was held by the Chartered Institute of Public Finance and Accountancy. So I've just copied their slides. So it seems quite reasonable. But we all know what's going on with regard to austerity. One of the things is that maintenance budgets for our infrastructure are being cut, although we're still doing quite a lot of capital spend, which we see in London, the Crossrail, for example. So this is one of the slides. You could summarize all those numbers by saying that in the next few years, from 2010 when this was written up to 2015, roughly a 25% cut in the available budgets to fix problems or to prevent them occurring. Climate change is a backdrop to this. Now, these two slides, which I downloaded only a little while ago from the DEFRA, the government DEFRA website, are very dense, but they're very helpful. They show predictions of change of precipitation, snow and rainfall, compared for the 2080, compared with roughly 1980. So the average 61 to 90, roughly 1980 to 2080. So in a century, this is what is going to happen if you take us a reasonable medium estimate of CO2 emissions scenario. And the left-hand one is the summer. Summers get drier. They get drier by between 17 and 28%. Let's call it 25%. So they get drier by about a quarter. And the dryness occurs in the southern England. So this will have a big impact on swell shrink problems, for example. Winter, it get wetter by roughly the same kind of number, about 25%, 14 to 26. And they get wetter, again, in southern England and in South Wales a bit there as well. Winter rainfall is what causes landslides, or what leads to landslides. So this time of year now, we're in maximum landslide occurrence period. We've had a nice wet autumn, wet winter. There's no leaves on the trees to suck water out of the ground. So it's getting nice high water tables. Landslides occur more frequently this time of year. So this is what's going to happen. But there's another thing, apart from drier summers and wetter winters, is increased storminess. So we're going to get big storms. And we saw that last year, and I was amazed when I saw this graph, this map. Now this one, which is from the Met Office, looks at the change in the amount of rainfall we had last year compared with a 30-year average from 1981 to 2010. If it's white, the rainfall last year was broadly the same as the average. If it's brown, it was drier than the average. And if it was blue, it was wetter than the average. What fascinating about this is that places that we know are really miserable and wet, like northwest Scotland, are drier. And places that are traditionally dry are wetter. So up in the northeast here, up through Northumberland, Durham, up to Scotland, was significantly wetter last year. Now, these kind of storms can lead to different types of landslides. Debris flows, those hillside debris flows are particularly susceptible to this kind of very heavy, intense rainfall that these things seem to represent. I mean, the driest place in Scotland is here. Somewhere just to the east of Edinburgh is the driest place in Scotland, historically, but it had an enormous extra rainfall last year. So this is the increased storminess. So we're looking at unpredictability in our climate at a time of austerity. Now, small things lead to big problems. I've got two examples. They both happen to be railways, but it was simply because I found a nice picture and I could quote someone without doubt of being wrong. So here's a small landslide on a railway line near Chipping Sodbury. It's affected 3 railway lines, you can see them there, and there are a dozen people in that image, and there are 2,000 tons, which isn't a big landslide. You can see you get it in your back garden almost. It's a small landslide. But look what happens. It stops the railway line between London and South Wales. So a tiny landslide has a big impact. And this photograph's interesting also in another way. Get that in your mind, then look here. Is that where the previous one occurred? Is that the remedial measure for the previous landslide? I don't know, I've not worked here. So maybe that's the previous landslide, that's the one that's just happened. Where's the next one going to be? Just there, perhaps. So this is the challenge that we're faced with. It seems such a small thing, a cutting that needs to be maintained, but at a time of austerity, making decisions about what to do here are very important, particularly if small things lead to big consequences. Next one's a canal. This is the Great Western Canal. Photograph's a little bit difficult, so I added, this is the top of the canal, this is the bank, and it ruptured, and the water poured out of the canal, down here, and formed a lake. It's only a 100-foot gap. In new money, that's 30 meters. It's nothing. It's a tiny little gap. But because the canal has got an enormous body of water, the quantity of water that comes out in a flood like that is very large. And look what happened. 20 families had to flee their homes. Trains were disrupted, cancelled between Exeter, Taunton, Plymouth and Bristol. A small thing here. Now the problem here, makes this situation even worse, is that this is a man-made embankment. So the cutting is made by man, by engineers building the canal long before civil engineering or geotechnical engineering or engineering geology was really invented, except of course William Smith. But how to build an embankment was not really understood until the 1940s. So it's not an engineered structure, and if it fails, it can be catastrophic like this. Small things lead to big consequences. So what's the role of the engineering geologist in all of this? Well, I hope you've got the idea that what we need to do is get the geology right, get the geomorphology right. We need to assess hazards, and then we need to work with our engineering colleagues to find the solutions to those hazards. And Professor Burland at Imperial years ago came up with this triangle that really underpins what we do. We need to understand the ground profile, so that's major engineering geological input into that. We need to observe the behaviour. We need to know what the ground is doing, and we need to build an appropriate conceptual model of the ground, like those cartoon drawings I showed at the beginning, and an appropriate mathematical model for engineering analysis. But pinning this all together is the things in the middle of Burland's triangle. We need to understand precedent. We need to not be reinventing the wheel. We need to be empirical. We need to do what has been done before successfully and adapt it. In other words, we need to use well-winnowed experience. So what tools of the trade, what skills do engineering geologists bring to the game? We know about geological materials, we need to understand processes, and we need to produce a geological model. So we're going back in time a bit in this lecture. This is James Hutton, a Scottish gentleman who was the first man in the world to finally figure out that the world is very old. And he did it at this place called Sicker Point and a number of other places, in which he was able to show beyond doubt that the world is very old. And what he's done here, this is an angular unconformity. So these are very old rocks, which have been laid down flat and tilted and made vertical in the Caledonian orogeny, Caledonian mountain building period. They were then eroded away, and the sandstones on top were laid down and have subsequently been tilted a little bit. He had no idea what period of time separated these. He just knew it had to be a long period of time. So he's one of the founding fathers of our profession. And we now know, of course, that the gap is 80 million years, as I've put up there. But he didn't know. It was just clearly a long period of time. So deep time and understanding geological processes is fundamental to what the geologist does. Another example here, which is the glacial epoch that we're still in. The biggest glaciation that's happened in that epoch is the Anglian one, about 500,000 years ago. And the ice came to this red line, almost to our doorstep here in Burlington House, and not far north, and then to the north coast of Devon. The last ice age, actual ice age itself is the Devensian, which came to that orange line. Now this means that we can divide England and Scotland, and Wales and Ireland, into 3 big zones. To the north of the orange line, the glaciations are very recent, so the signs of glaciation are in the landscape all the way. There's deep glaciated valleys, fresh rock, you can see the glacial lakes, you can see the moraines. South here, this area was never glaciated, but it was very cold. Every time there was a glaciation, it was freezing there. Imagine mammoths, tundra, deeply frozen ground, and in between, There's glaciated sometimes, there's a mix of glacial deposits and deep, deep tundra effects, which means that all of these are affecting the near surface ground, and it's the near surface ground in particular that leads to landsliding. So the geologist has to understand processes, deep time, to understand how we engineer our solutions to the problems. In other words, we build a model. This is a geological map. It means that when you're standing on the needles, you know it's chalk. But geologists have to know a lot more than that, of course. We've got to know how it works out in 3D, 3 dimensions in the ground. Sometimes we drill boreholes, sometimes not quite as exotic a place as that, which is in the Republic of Georgia. And we build in our minds those kind of models you see top right, and we physically draw them out. They become fundamental to how we communicate. Observed behavior is important as well. And I've only got one example I want to show you, but I want to show you how it works. Exhibit A. When you drill a borehole, say 8 inches in diameter, you can put a plastic tube like this inside it. This is an inclinometer tube. It's very solid. Grout it into the ground, and in the tube are little grooves. I don't know if those can be seen. And in the grooves, in the vertical tube that we put into the borehole, we run this torpedo. The torpedo has little wheels there, and the little wheels sit in the grooves. The torpedo has instruments in it that allow it to measure tilt to an incredible accuracy. And if we look at the tilt, we can work out the movement of the ground. So we drill a borehole, we put many meters of this in the ground, orientate it carefully, perhaps with one set of cross going downhill and one across to look at the movement. And then we come back periodically with instruments like this, with inclinometers, to measure the movement. This is one done by a colleague of mine only the other day in Oxfordshire. A road embankment that started to fail, trying to understand the nature of the problem, we're putting in an inclinometer in that little borehole. And here we have a published example from Italy. So this is the cross-section of the landslide. Here is inclinometer number 8, I8, and it's gone down to some great depth, and the broad depth of landsliding is this dotted zone above. So where the red arrow is, it's all moving downhill. Now these are the results from inclinometer 8. So if we go from the bottom upwards, the borehole is 50 meters deep, so it's very deep, and this pipe, or the Italian version thereof, is grouted in right to the very bottom. Now, the measurements are measured over a 5-year period in this published paper, 2005 to 2010. And the instrument comes up here, and it's almost the same result. Maybe the hill is very, very slightly moving. The scale at the top is in centimeters, so that's 5 centimeters left to right. But suddenly, at about 7 meters down, there's an enormous shift. This is the bottom of the landslide. This is that failure surface. Perhaps this is one of these translational slides. So the inclinometer is picking up exactly where the movement's occurring. And not only is it picking up where it is, but it's picking up the movement over time. So you keep coming back maybe every 6 months to measure it repeatedly. And after 5 years, it's moved of the order of 4 centimeters. So this is the information that will enable us to confirm the model for analytical purposes, and also to think about whether it's a whoosher or a creeper. So these are questions we need to answer. How do we change our approach in this time of austerity? How should we spend our money, and what's our professional response? So the first thing I think we need to do, and this is what we are doing as a country now, is working out our priorities. We have some really critical infrastructure that holds our sophisticated society together. Without that sophistication of our society, we wouldn't be here today. So we do need to ensure the railways, the highways, as I've said there, the water supply, and the one I've forgotten, of course, is sewage. It's no good delivering water if you can't carry it away. All of these things are vital. And somehow or other, as a society, we have to figure out where we want to spend our money. And that's why I've illustrated this small problem, big consequence. That's the difficulty that engineers, civil engineers, are facing. These small problems can have large consequences. Training and professional development is vitally important as well. It looks as if all Atkins does is romp in the snow, doesn't it? This is in Turkey, actually. There's some colleagues of mine and Professor Dennis Brunsden, who's working with us there, talking about a particular landslide as it might affect a pipeline. So we're all learning from each other. That is really vital. And professional training, of course, as you well know, doesn't end when you graduate. It continues your whole working life. But we've also got to let everybody know. We've got to advise, we've got to inform and alert. And that would be my criticism of this drawing. It's very good, but what do you do about it? This is the drawing that begins to give the answer. If you've got a tree of height h, it needs to be more than distance d from your house. And there you see the shocking number. A long dry summer, 75 millimetres, 3 inches of vertical movement, the ground's going up and down, on swelling and shrinking ground. So here we're giving advice. This is what Clive Edmonds has been doing in Reading. This diagram, it's not an engineering drawing, but it helps people understand what's going on. It helps explain why they need to have temporary disruption to fill up the galleries with concrete or grout or pebbles, and explains why these crown holes appear in apparently random place underneath Field Road and unfortunately underneath people's houses. Let us now go to this drawing. I showed you the middle of this drawing. There's the rest of it. You see, the situation was even worse than I portrayed at the beginning. There's rock falls at the top. There's goodness knows what's going on. There was a mud flow at the bottom. Look at this. It's like Armageddon, isn't it? It's just dreadful. But what's interesting is it's an Australian hillside, and it's the Australians explaining to their public, Australian specialists explaining to their public what to do. Well, this is the bad situation, and they advocate doing this. Don't chop the trees down. Don't build your house on a cutting, put it on piles, on piers that support the weight into the white bedrock that is stable. Do not build a swimming pool that might rupture. Manage your drainage very carefully. And if you look, they're not really modifying the overall slope of the hill at all. They're not cutting or filling. If you need to cut or fill, make a proper engineered structure. Now, to engineering geologists and geotechnical engineers, this is blindingly obvious, but it's not obvious to the general public. We, as a profession, need to tell people how to do things. I've got quite a collection of these. This is an Australian one. There's a wonderful one from Hong Kong. And indeed, there's a great one from the Isle of Wight, telling the people of Ventnor how to manage their particular risks, because that's on a landslide zone. So my conclusions. Of course, they're yes, no, but, aren't they? No, we've got to keep our basic training, which is what I'm very keen on, that our universities are training graduates properly, that they understand the basics of deep time, of geological processes, that kind of thing. But we do need new approaches. We do need to be using new technology. For example, we have in another job we have in Turkey, we have those inclinometers, but we don't go there. We read the results in our office in Epsom. It's all done by telemetry over the internet back to our office. So we can do a lot of clever things that begin to save money. And then we do need to be sure about valuing our assets, being sure we know where to spend our money. And the but, of course, is climate change plus austerity. Is this a perfect storm? Is it going to make our situation much worse? Our methods of handling problems, our well-winnowed experience and empiricism were built out of a time where climate change wasn't happening seriously. The world is changing now, so we need to be able to cope with that as well. Thank you.
Well, thank you very much, David. I told you that was what would happen, didn't I? We've got a real insight there into what a huge number of professional geologists actually do, and I think, as I thought you might at the beginning, David, talking about something which people don't necessarily know is going on, but which does impact on their lives. And I think you've also really helped us understand why it's important that people do understand it, that the general public do, and that policymakers do, and that that's important for training the next generation of geologists as well. So we've got a bit of time for some questions. Who would like to start us off? This one right in the middle here, Naomi. Yes. Just if you would wait for the microphone to reach you. Thank you.
Thank you. Yes, I can imagine, easily imagine a situation where a geotechnical engineer puts forward a model and says, this is what will happen if you don't do X, Y, Z. And the owner of whatever it is coming back and saying, X, Y is okay, Z is too expensive, bring up a cheaper model. At what point can you avoid the sort of professional integrity of satisfying your customer and still remaining true to what you know is likely to happen? How much cost cutting is actually practicable?
Cost cutting, we might use another word, optimization might be a more... Nonetheless, yes, you're right, and it's a matter of educating, isn't it? My work, I seldom deal with the individual member of the public, but we deal with corporations or people who run the railways, say, who face this problem. And they often have skilled personnel on the other side, but the difficulty is the one you've described, where we think we know what's going on, and the person at the other end of the conversation doesn't really understand. So we have to go through this kind of process I've just described to you here. These are the types of so we take about landslides. These are the types of landslides that occur. You've got a type X in your garden or in the back of your factory, and we're going to go talk you through the options that you might choose to adopt. Obviously, if there's life and limb threat, then it's a different story. But if the building is just going to crack because the ground is swelling and shrinking, that's another side of things. It is difficult to explain, and all we can do is explain. They don't have to take our advice.
Okay, down here, Steve.
Hi, I was interested to see that, especially with austerity and with the importance of understanding the ground and grain model, that monitoring plays a big role in that. Can monitoring tell us when a creeper will become a whoosher?
Very difficult to do that. But the first thing is to try and decide which type of landslide you have got. So the big rotational slides tend to move fairly slowly. So you've got time to get out of the way, generally. The whooshers, it's much more difficult because they happen within minutes. Monitoring of those are very difficult. So in Hong Kong, for example, they know that the landslides occur as a result of the very big storms they get, where they get a metre of rain overnight. A metre of rain overnight, that is going to do a serious damage if somewhere is landslide prone. So what they do there is the Hong Kong government geotechnical engineering office and the Met office there get together and they declare what's called a black rain day. And the idea is you take personal protection there. You stay indoors, you don't go climbing on the hills, you don't stand at the bottom of big slopes. That's what you can do for whooshers. For creepers, though, the inclinometer is a really good tool, measuring surface movement using GPS technology, a version of the TomTom you have in your car. Watching movement, that can help. But neither of them work if you've got the wrong model. So if you think you've got a creeper, but actually you've misunderstood the ground so badly that it's actually a whoosher, no amount of monitoring is going to protect you.
Okay, down here, Steve. Thank you.
First of all, I want to thank you for your very, very interesting lecture. You have been speaking about the rotational and translational slides. My question is, these two kinds, the rotational and translational, what their speed, how differs their speed in the life, and how could it be possible measure, for example, in case of earthquake, how they behavior, and above all, they have to endure very probably different stresses.
They move at different speeds. A landslide will move, say we take a simple rotational slide of the sort that I showed you earlier on, it will move at different speeds in its life. So the first thing you might notice is cracks in the ground. So you might have, I don't know, maybe your house has got a cutting and a hillside above. You might be wandering the fields above looking for rabbits and seeing cracks beginning to develop in the ground. This is the ground starting to fail. Not failing completely, it's just starting to fail locally. Eventually those cracks will join up, they'll join up at depth, and then it will move. So the cracks might take 6 months to move. Only small, maybe millimeters per week. But then it will move more suddenly, maybe meters or two a day, as the big blocks start to move down. Once that happens, if the ground is sufficiently wet, the soil can mobilize itself into effectively a mud and start just flowing down at maybe a meter a week, something like that. But unfortunately, the whooshers are much more difficult to predict because they happen just like that. Now, the stress regime needs to be thought about for each of those, and the key thing is the shape of the failure surface. And that's where engineering geologists meet the geotechnical engineers, trying to understand the shape of the failure, and then we look at the balancing of forces, the putting of a big retaining wall, shall we say, at the bottom, to hold back the slope.
And in earthquake?
Oh, I'm sorry, yes. With an earthquake, we've got a number of problems. In a hilly terrain, an earthquake will shake the ground. It shakes the ground anyway, but rockfalls, of course, are a major response to earthquakes because it just shakes bits of rock off cliffs. Sometimes some ground actually becomes temporarily more stable in an earthquake, but only temporarily. But quite often, the ground will fail and it will move. And I've done a few of those situations like that, where the earthquake has been the final triggering factor that caused the failure. Because what it's doing, it's putting an extra load on the slope. It's putting a gravitational load due to the shaking. So it's additional stress, as you were saying, on the slope.
Thank you.
Okay, no, there's a question down here. Thank you.
I'd just like to ask the speaker what his views are about fracking and the dangers of fracking.
Oh my goodness. I actually have no views on that, partly because I am not an oil industry geologist. He's just outside my area of expertise. There are people within the GeolSoc who have that expertise, and Nick will tell you, I think we've published a paper that explains it, haven't we?
We have published a briefing note on shale gas, which you can find on our website.
Well, I think the risk has to be thought in a number of ways. I don't want to give an opinion because I'm not technically qualified to give you an opinion. However, the risk is in a number of forms. There's what is going on in the ground, and there's environmental impact. And we need to separate those so that the solution to whether or not fracking is acceptable or not is a multidisciplinary problem. It's not simply the geology, it's the groundwater, it's the surface impact. There are many other things that need to be thought of. I would like to stop there because I'm in danger of going outside. In fact, I'm in danger of breaking my code of conduct, which says that if you don't know what you're talking about, shut up.
I'm glad you said that before I had to. Just to add to that, the note we have on our website does exactly what David said. It focuses on the area that we think we have something as a geological community to comment on. The judgment as to what's the right thing to do, it needs to draw on a lot of different disciplines. So I think just as individuals need to be careful to speak about what they know about or shut up, so do organisations. And I think that's something that our society's worked hard to do and will continue to do so. So I'm sorry for that qualified answer. Okay, Steve, question down here.
You gave an example of the failure of a canal system with an embankment that was
made
yes. before principles were understood. So when something like that happens, would people look at the whole canal system and see where other examples might or perhaps happen that would affect other essential infrastructure and perhaps take some remedial action? I mean, is there a sort of programme? Because I don't know whether some of the canals are now in sort of trust status or, that fractured, or whether they're all within one group of...
Yeah, you touched on lots of interesting problems there. Yes, all our canals were built before engineering of earthworks, which is what we talk about, was done. And the problem there is that they're so heterogeneous. They're just built of whatever was to hand. So if we say put a borehole down here and we go 30 yards over there, it might be quite different because they were all built by hand. If you see those old pictures of the navvies digging by hand, wheelbarrows. So it's very difficult to characterize the ground. So we have to take a very general view of what's going on. And we might, for example, put in extra drainage measures to ensure that doesn't break. Or we if the slope is like that, we might flatten it off to make it flatter. But it is very difficult dealing with old infrastructure. And indeed, our railway network was built before engineering. I mean, the London Underground isn't underground. A lot of it's above ground, and it's on embankments and cuttings of the sort I showed you at Chipping Sodbury. There's a lot of that, and they're all made before engineering was done. And the people who are responsible for running them have a problem which they tackle by trying to understand what's going on and using precedent. The people who built the canals and railways are no longer with us, sadly, to ask.
Okay, I think we've got time for one more question. Sorry, where did you spot it?
Somewhere in the middle.
Right in the middle now.
Your cartoon side of the Australian one and also the Chipping Sodbury landslip seems to be a problem with different departments not speaking to one another. In case of Chipping Sodbury, I don't know, but a lot of embankments around London had naturally forested themselves, and so you've got the problems with leaves. So let's go along, clear up the leaves. Got portable electric saws, petrol saws, and you can clear cut something, and so there's no longer roots to hold the embankments. So if you've got different departments and not talking to one another in the same operation, let alone different organisations creating responsibilities, how do you, in the age of austerity and very little planning and communication, deal with this?
Well, the problem you've hit upon is one that has been exercising the railway authorities quite considerably over the last decade or so, and a lot of research has been done onto whether it's better to prune the trees, chop them down. The trees not only have roots that stabilise the ground, but they're also sucking water out of the ground. So they are stabilising the cuttings or embankments as well. Conversely, the trees and the leaves are a problem. So the railway companies have been getting together with engineering companies like the one I work for to try to figure out what is the best thing to do. And if you have to prune trees, can you put additional drainage in? Or can you plant additional trees of a different sort that aren't so problematical? But as with all problems, if you can recognise the problem exists, you're well on the way to solving it. And you describe the problem very well. And you'll see that on a railway network in London, say, that trees are being chopped down. But you'll also see that engineering work is being done at the same time in recognition of the effect.
Well, I think we'd better give our speaker